right, you're on.
Hello, I'm Doug Montgomery. I'm the host and organizer of our Design of Experiments MOOC, and I want to welcome you back to our Fireside Chat. This is the first one of this new academic year. For those of you that are new to the Design of Experiments MOOC or the Fireside Chat, this is a monthly event that I run, typically with a guest speaker to explore different topics, different applications of experimental design techniques. We always try to leave some time at the end for questions and answers. This is a great time for you to bring up questions and ask them. And they could either be about the Coursera course itself, or it could be to a specific situation that you're running into, or it could be something a question that is motivated by the guest, something that they talk about that stimulates your interest. For those of you that are on Coursera, we actually post these Fireside Chat recordings to the courses. You'll find them in the resources tab of your course, and all of them are there. And I think we've done something like 27 or 28 of these. So you've got a big repertoire of things to look at, lots of interesting topics, lots of interesting guests. So I definitely encourage you to take a look at the material that's there. Okay, so a little reminder about how we're trying to do this. Please continue to keep your microphones muted, your cameras off during the session to prevent any sort of extraneous noise from entering into the system. If you want to submit a question to either me or the guest, use the chat function on the Zoom menu to do this. And you can do this anytime during the presentation. You don't have to wait until the Q&A begins. You can submit your question any point during the Fireside Chat. We try to get to all of these during our live session. But if we don't get them answered during this time, we'll respond to it in Coursera for those of you that are actually enrolled in the course. So eventually we will try to get to every question that we have. Okay, so our guest today, I'm very pleased to have Peter Goos as our guest. He is a full professor in the Faculty of Bioscience Engineering at KU Leuven University, and at the Faculty of Business and Economics at the University of Antwerp. Peter teaches courses in both introductory and advanced topics on statistics and probability. His primary research area is statistical design of experiments. He has published a lot of really interesting papers in different journals, both statistics journals and engineering and science journals. He's the author of 2 books. The Optimal Design of Blocked and Split Plot Experiments. This is, I think, quite a revolutionary book. And the a book on optimal experimental design, a case study approach that he co-authored with another guest on our Fireside Chat from some time back, Brad Jones from JUMP. Peter's work has been recognized with lots of awards. He's received 4 Schul Awards, 2 Lloyd Nelson Awards, and a Brumbaugh Award from the American Society for Quality. He got the Ziegel Award and the Statistics and Chemistry Award from the American Statistical Association. So his work is well recognized. He's a well-published, well-recognized scholar in the field. He's also a co-founder of EFFEX, which brings a whole new web-based design of experiments software to the market. And Peter, I'm really anxious to hear your talk today. I think this is a fascinating topic.
Thank you, Doug, for the introduction. I will now share my screen, and with a little bit of luck, you see it.
Yep. Looks good.
Great, thank you. So as a topic for today, I chose OMARS designs, screening and response surface experiments in one. And I should get rid of this, I think. So all of you probably know that in industry, experimental studies often involve 2 steps. The first step is typically a screening experiment. And the screening experiment is then followed by a response surface experiment in which you typically build on the knowledge acquired during the choice experiment. So traditionally, experimentation has been sequential in industry. And this has worked very well for many, many decades already. But there are at least two drawbacks. The first thing is that when you want to perform a screening experiment and later on a response surface experiment, you need to get approval for two experiments from your superiors. The second drawback is that inevitably some time goes by between the initial screening experiment and the follow-up response surface experiment. And time is, of course, very precious, especially nowadays that we live in a very competitive environment. And for example, in the pharmaceutical and chemical industries, there is increasing pressure to shorten the time to market. So therefore, that sequential strategy may be too time-consuming to be ideal for example, the pharmaceutical and the chemical companies. Now, how can you shorten the time to market? Well, perhaps we can combine a screening experiment and a response surface experiment in one. And that's going to be the topic of today. How can we achieve a combination of screening and response surface experimentation in just a single experiment? First of all, a little rehearsal, perhaps. Screening experiments, the typical first stage of experimentation, is intended, screening designs are intended to identify the vital few among all the factors that might influence the response or the responses you're interested in. Classical screening designs study all the factors at two levels, and usually this is done with a limited number of tests. The best known screening designs are full factorial designs, fractional factorial designs, and Plackett-Berman designs. And of these three kinds of designs, I put full factorial designs between parentheses because full factorial designs are only feasible if you have a very limited number of factors. For real screening designs, which may have 6, 7, 8 or more factors, full factorial designs are typically out of the question, and we have to live with fractional factorial designs and Plackett-Berman designs. All of these designs have very nice mathematical and statistical properties, and one of the important properties that these designs have is that they are orthogonal for the main effects. They allow you to estimate all the main effects independently. So that's very good, but there's also a few worrying things about small screening designs, especially, and that is, if you go for really small screening designs, there is oftentimes substantial aliasing involving all the two-factor interactions. And for really small screening designs, that aliasing is even present between the main effects and the two-factor interactions. Because you often want to know also whether there might be quadratic effects, people typically add center runs to these two-level screening designs. These center runs allow you to figure out whether there is one or more quadratic effects somewhere out there. But with this approach, you can never identify individual quadratic effects. In the second phase, then, we switch typically to response surface designs. Response surface designs are marketed as experimental designs for process optimization, and you usually do them after the screening experiment, after you have figured out which are the vital few factors. And in the response surface experiments, you typically focus on those vital few factors. Response surface designs allow you not only to quantify the main effects, but you can also estimate all the quadratic effects individually, and you can typically also estimate all the quadratic effects individually. The best known response surface designs are central composite designs, CCDs, and Box-Beinken designs, BBDs. These designs also have very good mathematical statistical properties, these designs are perfectly orthogonal for the main effects. In addition, they are perfectly orthogonal for the two-factor interactions as well. And the main effects are orthogonal to the two-factor interactions and to the quadratic effects. So basically, you can estimate the main effects and the interaction effects independently from each other, which we like. These designs also offer you large powers to detect main effects and to detect two-factor interactions, another good property. Less good is that the number of tests required by central composite designs and Box-Beinken designs increases quite rapidly with the number of factors. So if the number of vital few factors is quite large, you end up with very big central composite designs and very big Box-Beinken designs, and so also very expensive and time-consuming designs. But at this large experimental costs, you are guaranteed to have a painless data analysis because the design is so beautiful, because you can estimate most of the effects independently from each other. These nice properties that classical response surface designs have can be summarized in a color map on correlations. This color map on correlations you see here is for an 8-factor central composite design. And you can see that this color map is very blue. The blue basically means that there's a lot of orthogonality, that you can estimate many effects independently from each other. For example, the top left part of the color map looks perfect, meaning that you can estimate all main effects independently from each other. The next part of the color map is also perfectly blue, and that is because you can estimate all the main effects independently from the interactions and also independently from the quadratic effects. So another great property. The central part of the color map is also nice because with classical response surface designs, you can estimate all the interactions independently from each other. And because the central right part of the color map is blue, you can estimate the interactions also independently from the quadratic effects. And the only thing you can't estimate independently are the quadratic effects. That's why the bottom right part of the color map is not perfectly dark blue. But so that's the typical look of a great color map on the correlations. And it comes, if the number of vital few factors is not negligible, it comes at a quite large cost because central composite designs and Box-Beinken designs get large if more than a few factors matter. What can we do about this? Well, first of all, in 2011, definitive screening designs entered the DOE arena. Definitive screening designs have been developed by Bradley Jones on the right in this picture and Chris Nachtsheim on the left in this picture. And these designs have become very popular very rapidly. Now, why is that? Well, of course, because definitive screening designs have attractive properties. On this slide here, you can see one example of a definitive screening design. It's a definitive screening design for 8 factors. You can see that the design involves 17 runs. So that means that this particular definitive screening design allows you to study 8 factors with just 17 runs. So with a rather cheap experiment. What is typical about the definitive screening design? Well, first of all, it has 3 levels for every factor. And that's very unusual for something called a screening design. Well, these 3 levels for every factor in a definitive screening design allow you to estimate all quadratic effects independently. I mean, separately from each other. Another thing is that every even numbered row of a definitive screening design is the mirror image of the preceding odd numbered row. And because of that, because of that, you can estimate the main effects independently from all the interactions and from all the quadratic effects. And that's another nice property that classical response surface designs also have. And finally, I should add that definitive screening designs are perfectly orthogonal for the main effects as well. So definitive screening designs, despite their small size, they have many of the good properties of the larger classical response surface designs. And these properties, these attractive properties of definitive screening designs, are also visible in these color maps. This is the color map for the 17-run 8-factor definitive screening design I've shown you. First of all, the top left part of the color map is perfect again, because the design is orthogonal for the main effects, so you can estimate all main effects independently. The top right part looks perfectly blue, meaning that all main effects can be estimated independently from the second-order effects, so independently from the interactions and the quadratic effects. And that's where the good news stops. So there is good news, but then there is also a bit of bad news. In the central part of the color map for the definitive screening design, you can see that there are shades of pink. And that is because the interaction effects are sometimes strongly aliased with other interaction effects. So when it comes to interactions, definitive screening designs are not perfect. Also, there is some aliasing going on between interaction effects on the one hand and quadratic effects on the other hand. So to summarize, there is some good and some bad news in this color map. There is some perfect dark blue, meaning perfect orthogonality, independent estimation, but not for the interactions in the central part of the color map. All of this is summarized on this slide as well. So definitive screening designs, which we often call DSDs, have nice orthogonality properties. Main effects are orthogonal to each other. Main effects are orthogonal to two-factor interactions and to quadratic effects. And therefore, they are orthogonal and minimally aliased. This minimally aliasing property is a term. That's a term we typically use whenever a design has its main effects orthogonal to the two-factor interactions and the quadratic effects. So all of this is very nice. In addition, as I pointed out, you can estimate individual quadratic effects with a definitive screening design. Also, cost-wise, definitive screening designs perform well because the number of tests required by a definitive screening design only increases linearly with the number of factors. And therefore, definitive screening designs have fewer runs than classical response surface designs. So all of that is good news, but I pointed out in the color map that two-factor interactions can be very strongly aliased with each other. And therefore, it's sometimes hard to figure out which interactions matter and which interactions don't matter. Similarly, two-factor interactions are sometimes strongly aliased with quadratic effects, and therefore sometimes it's hard to figure out whether it's an interaction that matters or whether it's a quadratic effect that matters. So for definitive screening designs, there's good news and bad news. And if you have bad luck with your definitive screening experiment, and there are more than a handful of important factors, then your analysis can be painful and leave you with ambiguity due to that strong aliasing between the interactions and the quadratic effects. So that is especially if you have bad luck and a lot of factors matter. If you have good luck, however, and only a few factors matter, Then definitive screening designs project onto a response surface designs in those few important factors. And because if that happens, if only a few factors matter, then basically your definitive screening design becomes a screening design and a response surface design in one, and you don't need to perform an additional new response surface experiment. And that's, of course, together with the low cost of definitive screening designs, a very important selling point in favor of definitive screening designs. Some people therefore view definitive screening designs as a small Because of this, definitive screening designs can be viewed as the smallest kind of response surface design there is. What I should also add is that, despite the fact that it serves as a small response surface design, and despite the fact that you can estimate individual quadratic effects, I should point out that the power for detecting quadratic effects with definitive screening designs is not very big. And that's because definitive screening designs only have a limited number of zeros for every factor. So with definitive screening designs, it's only the very big quadratic effects that you can detect. So as a conclusion for this overview of classical experimentation and definitive screening designs, I can say that on the one hand, we have traditional response surface designs with attractive properties, but unfortunately with a lot of runs, which you often have to do after you've already performed an initial screening experiment. On the other hand, at the other end of the spectrum, you could say, we have definitive screening designs with a very small number of runs, with some attractive and some unattractive properties. We saw that in the color map. And these definitive screening designs, they can function, if you're lucky, and only a few factors matter, as a screening design and a response surface design in one. Now, having observed, these two extremes, traditional response surface designs on the one hand, definitive screening designs on the other hand, having observed that, we wondered in our research group whether designs exist with similar orthogonality properties as these traditional response surface designs and these definitive screening designs, but with an intermediate number of runs. So is there a family of designs that bridges the gap between the definitive screening designs, which are sometimes a bit too small perhaps, and traditional response surface designs, which sometimes are too big? Well, the answer is yes. There exists a whole family of designs bridging that gap between DSDs and response surface designs. And that new family of designs, we call them orthogonal, minimally aliased response surface designs. And you can abbreviate that as OMARS designs. Orthogonal, minimally aliased response surface designs. You may have heard that I used the word we. I did not discover the OMARS designs alone. I had a co-author, I had a partner in crime, and that partner in crime is José Núñez Ares. He's on the right on this picture. I'm in the middle, of course, but José is the first author of all the papers about these OMARS designs, these orthogonal minimally aliased response surface designs. The OMARS designs are three-level designs, just like the DSDs. So 3 levels for every factor. And therefore, we call them response surface designs, because as soon as you have 3 levels per factor, you have a chance to estimate a traditional response surface model with main effects, interaction effects, and quadratic effects. So that's where the RS in OMARS comes from. In OMARS designs, all the main effects are orthogonal to each other. And because the word orthogonal starts with an O, we have here an explanation of the O in the name OMARS designs. And that leaves only the MA to be explained. Well, in OMARS designs, all the main effects are always orthogonal to the two-factor interactions and to the quadratic effects. That's the minimal aliasing property I pointed out before. So because OMARS designs do have that extra orthogonality property between the main effects and the second order effects, we also call them minimally aliased. And if you put that all together, you have orthogonal, minimally aliased response surface designs. Now, how many of these OMARS designs exist? Well, quite a few. When we made our first attempt with, say, a basic algorithm to search for OMARS designs, we found a few thousands of OMARS designs. For example, for 3 factors, we found 5 different OMARS designs with numbers of runs ranging from 8 to 14. For 4 factors, we found 41 OMARS designs with numbers of runs ranging from 8 to 24. And you can see in the right-hand column of the table, the rightmost column, you can see that for 7 factors at the time, we found 1,082 different OMARS designs, the smallest of which had 14 runs, the biggest of which had 70 runs. Most of the OMARS designs we found had an even number of runs and were fold-over designs. That means that most of the OMARS designs have, the even numbered runs are the mirror image of the preceding odd numbered runs, just like the definitive screening design that I showed you. Some of the OMARS designs we found were not fold-over designs, but that was a minority, as you can see in the table. And some OMARS designs had an odd number of runs. Now, that was our first attempt, and that work is published in a technometrics paper from a couple of years ago. Now, we worked on our initial algorithm to search for OMARS designs. We improved the algorithm week after week after week, and we found more and more OMARS designs for more and more factors. And you can see in this table, for even numbers of runs, how many OMARS designs we have found in the meantime. And you can see that some of these designs allow you to study 12, 13, 14 factors with a very limited number of runs. But there are also designs with a little bit more runs, so to bridge the gap between definitive screening designs and the classical response surface designs. Now you may say, well, it's very nice for you that you found so many of these OMARS designs, but are these designs any good? Well, we compared the OMARS designs to benchmark designs, and we found that many of the OMARS designs possess attractive properties. And many of our comparisons are between OMARS designs on the one hand and definitive screening designs on the other hand. And we can see that very often for the same cost or similar cost, there's an OMARS design that outperforms definitive screening designs. For example, what I show you here is the color map for an OMARS design with 22 runs, 5 factors on the left-hand side. And on the right-hand side, you can see a definitive screening design with the same number of runs, also for 5 factors. And you can see that in the color map on the left, there is less pink than in the color map on the right. So that means that the interactions are less strongly aliased with each other when you use the OMARS design than when you use the definitive screening design. We also made other comparisons. For example, we compared the powers for detecting effects with the OMARS design and with the definitive screening design. And what you can see is that the blue bars, let me take my pointer. The blue bars for the quadratic effects are higher than the purple bars for the quadratic effects. And that's because the OMARS design has substantially bigger powers for detecting quadratic effects than the definitive screening design. So the blue bars are for the OMARS design, the purple ones for the definitive screening design. You can see that for the main effects, the definitive screening design is a tiny little bit better. So you have to give in a little bit of power for the main effects, but you gain quite a lot of power for the quadratics. There are similar other comparisons that we can make, and the OMARS design does very well compared to the definitive screening design. This is, by the way, the 22-run 5-factor definitive screening design, the 22-run 5-factor OMARS design. And you can see that it's a 3-level design, nothing really magic about it, but it has a bit more zeros than a definitive screening design typically has. It also is a fold-over design, so it shares many of the properties with designs that you know, but it's a bit better for detecting quadratic effects, and it has less aliasing among interactions. Now, in the meantime, we generated many OMARS designs, and a few have been used already in industry. For example, in an electricity producing company here in Belgium, OMARS designs are used to perform nuclear waste storage experiments. And what you see here is a color map for a 27-run OMARS design for 10 factors. And you can see that despite the small size of the experiment and the large number of factors, there is no pink in the color map, meaning that there is no super strong aliasing among interactions or between interactions and quadratic effects. So these are very good properties. What else can I say about this ambitious nuclear waste storage experiment, 27 runs, 10 factors? Well, that design, that OMARS design, has a large power for detecting quadratic effects, substantially larger than any competing definitive screening design. And if at most 4 factors would matter in the end, if there are 4 factors you really care about in the end, then the OMARS design would allow you to estimate any response surface model in these 4 factors. So regardless of which factors matter. Because of this property, we say that the OMARS design has a projection estimation capacity for 4 factors of 100%. You can estimate 100% of all models with 4 factors of the original 10. And that's not true for the competing designs. For example, benchmark definitive screening designs only allow you 33% or 73% of all the subsets of 4 factors. So as you can see, the OMARS designs have attractive properties, and because of this good projection estimation capacity of the OMARS design, you have a better chance that a single experiment suffices if you use the OMARS design than if you use a definitive screening design. So you have a better chance that you can do screening and response surface experimentation in a single step when you use the OMARS design. Of course, we don't sit still in our research group. We continue to work on the OMARS designs because we believe they are promising. And we have extended the original family of OMARS designs from so-called uniform precision OMARS designs to non-uniform precision OMARS designs. Our original designs had the same number of zeros in every column. Well, now we have relaxed this requirement and we allow the different columns of an OMARS design to have different numbers of zeros. This is important if for certain factors you want to pay more attention to quadratic effects than for other factors. We have also generated strong OMARS designs in which the two-factor interactions are also orthogonal to each other and orthogonal to the quadratic effects as well. These strong OMARS designs have the exact same kind of color map as the traditional response surface designs. So they have basically, they're almost perfectly blue for all the effects we care about. We also generated mixed level OMARS designs, and that is because sometimes you may want to study two-level categorical factors. Well, it turns out that you can combine three-level quantitative factors and two-level categorical factors in mixed-level OMARS designs. And we also found a method to arrange OMARS designs in blocks so that you can estimate the main effects independently from the blocks, and we call these designs orthogonally blocked OMARS designs. So these are some of the more recent evolutions. I don't have time to go into all of these in this Fireside chat presentation, but I do want to show you that, companies already use these OMARS designs nowadays. For example, W.L. Gore has used one OMARS design lately for a heart valve experiment. At W.L. Gore, researchers know their processes very well, so they have quite a lot of a priori knowledge for every single experiment that they do. And for the heart valve experiment, they wanted to study 8 factors in total, and some of the factors W.L. Gore wanted to study at 3 levels, other factors they wanted to study at 2 levels. And you can see that in the one but last column of this table, where the number of levels for each of the 8 factors is shown. Some factors 3 levels, other factors 2 levels. And that's due to that a priori knowledge that they have. They know that certain factors are likely to have quadratic effects and others not. They had similar a priori knowledge about interaction effects. They suspected certain interaction effects to be very important, and they knew other interaction effects to be not important at all. And all that a priori knowledge they summarized in this kind of table here, where you can see a few letters H. The letters H mean high priority. These effects are likely to be important. And what I highlighted now by means of these red squares, these are the 5 quadratic effects they thought would be important in the end. And because these 5 important quadratic effects were expected for x1, x2, x5, x6, and x8, these 5 factors were studied at 3 levels. The other factors were not suspected to have quadratic effects, and therefore they were only studied at 2 levels. You can also see that there are a few letters H off the diagonal of this table, and that's for the interaction effects that W.L. Gore expected to be important. You can see that they expected the interaction between x3 and x4 to be important, the one between x3 and x5, the one between x4 and x5, and finally the one between x6 and x7 to be important. Now, using that a priori knowledge of the W.L. Gore subject matter experts, we went to look for an ideal OMARS design for their case, and we found a design with 24 runs, in which 5 of the factors were studied at 3 levels and 3 of the factors were studied at 2 levels. In the table I show you, you can see that 3 columns are colored dark blue. They are the 2-level factors, 2 levels only, -1, +1. The light-colored columns have 3 levels each. They involve -1s, 0s, and +1s. So for the light-colored columns, quadratic effects could be estimated, which was not the case for the dark-colored columns of this design. Now, how good was that OMARS design? Well, here's the color map, focusing on the main effects, and the quadratic effects and the interaction effects W.L. Gore expected to be important. And you can see that that color map is quite blue. There's no pink anywhere, only some gray and some light blue. So that means that there is not a tremendous amount of aliasing among the second order effects that W.L. Gore expected to be important. And for the rest, the design was perfectly orthogonal for the main effects, and all the main effects were orthogonal to all the second order effects. So that design was successfully used by W.L. Gore lately. And that brings me to the end of my presentation about OMARS designs, which for most of you were new, I guess. Well, you've seen that OMARS designs look promising, and my collaborator, José Núñez Ares, the co-inventor of OMARS designs, is now trying to valorize these OMARS designs. He established a spin-off company of the University of Leuven named EFFEX, short for efficient experimentation. And his goal is now, this is José, his goal is now to bring the OMARS designs to the market, to bring the OMARS designs to the DOE users. To this end, José has selected the best OMARS designs among all those we found. He looked at all possible criteria to identify the best possible OMARS designs, and he selected the so-called Pareto optimal OMARS designs. That basically means these are designs that perform well with respect to multiple criteria for selecting designs. And right now in his software, which is web-based software, in his web-based software, 500,000 OMARS designs are available. So that's a little plug for José's work and his web-based design of experiments software including these OMARS designs. So that brings me now really to the end of the talk. I do have a few references here. These are the 3 papers we published so far about OMARS designs. There is the very first paper in Technometrics from 2020 about 3-level OMARS designs. We extended this by adding 2-level categorical factors in 2023 in a paper in Statistica Sinica. And José and I, we also published the method to create orthogonally blocked OMARS designs, and that is published or is going to be published in the Journal of Quality Technology. I thank you for your attention.
Peter, thank you very much. This is an extremely interesting talk, and I have read a little bit about these designs, but there, you pointed out quite a number of things that I was not familiar with, like the method for blocking these designs is quite nice. One question that I had before we get to the participant questions is, what about the analysis? What sort of analysis method do you use for these OMARS designs?
Well, I have 2 answers to that. First of all, any method that you can use for a traditional screening design. And for a traditional response surface design, you can also use for OMARS designs. But I can also add to that because of the nice structure of these OMARS designs, you can perform an analysis similar to the fit definitive screening design analysis that Bradley Jones and Chris Nachtsheim developed for definitive screening designs. You can use a very similar methodology for OMARS designs. And in that methodology, you first identify the most important main effects, and then in a second stage in the analysis, taking into account heredity or not, you can then select interaction effects and quadratic effects.
Yeah. I was guessing that as a novice idea, you might try something like two-stage stepwise regression. Fit the main effects first, and then try to add interaction terms and quadratic terms involving the significant main effects.
That's basically a summary of the method of Jones and Nachtsheim for definitive screening designs.
Yeah, and I was guessing that something like that would probably work pretty well here. That's it. But is analysis built into this software that you've mentioned? Is it strictly a design generation tool?
So for the time being, it's a design generating tool, but I think Jose has a plan in September to also provide analysis.
Okay, that would make it extremely useful.
Definitely.
Yeah. Does he host this software on a particular website or?
Yes. The website is EFFEX.app.
Oh, okay. So
the exact link was mentioned on the one slide I showed about the software.
Okay, good.
EFFEX.app.
Good. That's
and if I can add a little to that, perhaps the name EFFEX. The name EFFEX is quite subtle. I said it means efficient experimentation. That's of course clear. Everybody wants to be efficient in his or her experimentation. But you perform experiments to detect effects. And in America, when people pronounce the word effects, it's often as effects. So there is some kind of subtlety in the name of the software there too.
Yeah, I caught that. I thought that was very clever. I really thought that was quite clever. We have some questions. Let's see. Peter, the first one says, suppose in two-factor experiments interaction effect is significant, then how do you analyze and interpret this result? If interaction and main effects both are significant, can we still discuss the main effects too? My thought on this, and feel free to comment here, but my thought is that if you have a significant interaction effect, the interpretation of the individual main effects is not as straightforward. You actually need to take the interaction effect into account in determining the effect of the individual factors. You may find, for example, that the individual factor temperature has a strong positive effect at one level of maybe ingredient concentration, but at the other levels of ingredient concentration, the temperature effect may be different. And so you really have to interpret the main effect in light of how it interacts with the other factor or factors.
What I like to do in that case is create a contour plot.
Yeah.
To fully understand the relationship between the two x's and the response.
Yes, if both factors are quantitative, a contour plot is great. Even just a standard two-factor interaction plot can help a lot with that. There's no doubt about it. But contour plots are also a great aid in interpreting these effects. And of course, if the interaction effect happens to be a three-factor interaction, then you can have a contour plot at different levels of the third factor. And that can also be extremely useful. Good question. It's a good question. Okay, here's number 2. I'm trying to screen the significant parameters which are affecting silver nanoparticle synthesis. I have isolated 6 factors from the literature which have an effect on the N nanoparticles. Question is, I'm not sure whether the response will be linear or it will have curvature. So if I run Plackett-Berman screening, how can I determine whether my response data will have curvature or not? If not, can I run a factorial experiment itself to screen significant parameters for further optimization using RSM? Well, you can always add center runs to a Plackett-Berman design, and that would allow you to test for curvature. But I would think that this problem is one that's kind of setting itself up for either a DSD or an OMARS design, don't you think?
I fully agree with you, Doug.
Yeah, I mean, the number of factors that you have is relatively small, only 6. And so you could be looking at a design with maybe well less than 20 runs. And that would be maybe an attractive approach to dealing with this. I would think the OMARS design or the DSD, either one would be an ideal way to tackle this problem. It doesn't say that the factors are quantitative, but if certainly if most of them are quantitative, this would seem to be a reasonable approach.
Especially now that OMARS designs and definitive screening designs exist with
Yes.
3-level quantitative factors and 2-level categorical factors too.
Yeah, this would seem to be an ideal situation for that. I'm having some personal experience with gold nanoparticles. I have a research project, Peter, with people at the University of Arizona Medical School and at the University of Nevada, Reno Medical School, and with people at Duke University, and we're developing a diagnostic device that can be used in the field with military troops to detect the presence of any of the Class A pathogens that the Defense Department is worried about people weaponizing. These are things like anthrax, something called Rift Valley fever, because some of these are really dreadful things that can be weaponized. And we're using gold nanoparticles to increase the sensitivity of the antigens that are used to detect these different pathogens. And so the people at Duke University are involved in building these gold nanoparticles, which is quite an exciting process. So I'd be interested in this experiment myself. So if the individual that shot this question and wanted to share some more details with me, I'd like to hear about it. So feel free to send me an email and tell me a little bit more about this. I'd like to know a little bit about what your factors are and what you're thinking about doing. Interesting question. Okay, there are mathematical expressions backing up the number of experimental runs of some designs, full factorial, fractional factorial. I want to find out if there are established mathematical formula that determine the number of experimental runs, the various mixture process designs, such as optimal combined designs and optimal custom designs. Question is necessitated by the arguments of reducing the number of experimental runs to economic sizes. In addition, OMARS designs is of interest to me. Are there literature materials for me to learn the details of these designs? And I think the answer to that part of the question is the papers that you cited.
Yes.
Yeah, and
yes, we have 3 published papers on the construction of OMARS designs, and I all listed them in my one but last slide. We also have a paper about the analysis method we talked about 5 minutes ago.
yes,
the two-step analysis method. That is also published in Journal of Quality Technology. Feel free to drop me an email if you want me to send you the papers.
That would be great. I'm trying to remember, are the citations to those, they're on your slides, but do they get posted as part of the as part of the Fireside chat recordings in the MOOC? But people that even if the slides aren't posted, if they watch the MOOC, your slide is contained in the video recording, and so the citations to those papers are there. So you'd be able to track those down, I think, without any trouble. The first part of the question is kind of interesting. You definitely run into the sample size number of runs question when you're dealing with mixture experiments and mixture process variable experiments, because take the basic simplex design. The basic 3-2 simplex design has 6 runs. Okay, well, you're going to do more than 6 runs, so you're going to replicate some of those runs. Well, how many? How many runs do you replicate? And a lot of that is judgment. How large you think the effects are, and there's that's always a question when you run those designs. There aren't fixed formula that determine how much replication you actually need. It's a function of how big the effects are that you're looking for. It's probably the same as somewhat true with OMARS designs and DSDs as well.
The mathematics for mixture experiments is a bit harder because these designs are not orthogonal.
Yes.
While for classical designs and definitive screening designs and OMARS designs, they are to a large extent orthogonal, and then the mathematics is much easier.
Yeah. I can remember talking about this question with mixture designs with John Cornell years ago. John, I don't know if you know this, Peter, but John was my next door neighbor in graduate school. And so John and I knew each other for many years, and we were great friends. We played a lot of golf together when we were graduate students, and I can remember asking him about the famous yarn experiment that he wrote about, which was an experiment that he ran when he was still working in industry at Tennessee Eastman, where they were blending 3 different types of yarn for drapery fabric, and they ran a simplex design, and they replicated the vertices twice, and they replicated the centers, the midpoints of the edges, the flats 3 times. And I said, John, how did you decide to do that? And he said, well, nobody had any idea about what to do. But he said, the engineering people told me that when you blended these fibers together, you probably got more variability than when you did the single fiber. And so he said, I decided to replicate those runs more, just because there might be more variability. And, you make those kind of decisions. Have you thought any about augmenting strategies for these designs, the OMARS designs? For example, you run the experiment, and you have some ambiguity now about certain effects. Would you consider augmenting the design in some way so as to give you more information about certain effects, maybe to de-alias?
Sure. What I would recommend is to use optimal experimental design for the follow-up experiment, focusing on those effects that are aliased with each other.
Yeah, add those runs to your model, and then find which additional runs would be required to.
Yes, indeed.
Great.
Yes.
Peter, this has been a fascinating chat. I really have enjoyed this a lot. I think this is an important development in experimental design that you and your colleagues are putting forward. I want to thank you again for taking time. I know it's getting to be dinner time or later for you at home, and I do appreciate you doing this. This concludes our Fireside Chat for today. Our next Fireside Chat is going to be on September 27th, and our guest is going to be Katie Brickey from Pfizer, and she's going to give a really interesting talk that I think you'll enjoy. You can find, as I said, all the recordings for our past Fireside Chats at the Resources tab in Coursera. Look forward to seeing you next month for our next Fireside Chat. And Peter, thank you again very much for a wonderful talk.
It was a pleasure.